What is a Cauchy sequence? Well, here's the definition written out in standard mathematical shorthand here. Xi is a Cauchy sequence if for all epsilon greater than 0 there exists an n such that mod xj minus xk is less than epsilon whenever j and k are greater than n. Okay, right. So what does that mean? It means if you give me an epsilon, I can find an n, and any pair of numbers in the sequence which lie beyond n, the distance between them is going to be less than epsilon. Okay, so for example, we've got this epsilon here, and n could be probably, let's see, 1, 2, 3, 4, 5, anything from, I don't know if that's in or out, or that one for that matter, but you don't have to be exactly on the nail. 10 will do. So if you give me that epsilon, I could say 10 for n, and then everything from 10 onwards, any pair of them differ from each other by less than epsilon. Okay, that's all it means. So you give me an epsilon, I give you an n. Right, well, what that means is that for a start, every Cauchy sequence is going to be bounded above and below. That means it can't go to infinity. And why is that? Well, I choose what? Epsilon to be, say, a tenth, and that'll give me an n. And then every member of the sequence up to n, there's only a finite number of them, so there must be a maximum and there must be a minimum. And then all these beyond 10 are all within 1/10 of each other, because I've chosen epsilon to be a tenth. So the maximum plus a tenth is the greatest it could possibly be, and the minimum minus a tenth is the least it could possibly be. Now that's if the sequence was continuously increasing or continuously decreasing. So it's definitely bounded. And of course it converges, or at least it appears to converge in R. It does anyway, as we will see. So what do we use Cauchy sequences? Well, we want to be able to talk about convergence without having to actually specify what the limit is. Because if you don't know what the limit is, it's in the conventional description of a sequence converging, you have to know what the limit is and say it approaches the limit and so on, and therefore it's convergent. But if you've got Cauchy sequences, you don't need to specify what the limit is. So you can talk about convergence without knowing what limits are involved. And that's why it's useful to for filling in these gaps in Q and constructing R from it, as we'll see. Right. Okay, this is what we do. We define every real number as kind of like the limit of some Cauchy sequence in Q. And of course there's going to be many Cauchy sequences defining the same real number, but this is not a problem, as we'll see in a minute. Right, here's, for example, is a Cauchy sequence defining pi, and it's, as you can see, it's a very convenient sort of sequence. And this is like the conventional decimal expansion of pi, and I think that's all it is. And indeed it is a Cauchy sequence, because if for example you give me an epsilon of, say, 100th, then I can find an n, and in this case it'll probably be this one here, any 1, 2, 3, any number greater than any number in the sequence beyond this point here is going to differ from any other by less than 100th, as you can see. I mean, it's pretty obviously a Cauchy sequence. Okay, here's two Cauchy sequences, both defining the square root of 2. Now this is the first one, which I got from the previous continued fraction, and this is a much more convenient one to work with. And if you think about it, when are two Cauchy sequences going to be the same? Well, pretty obviously, if the limit as n tends to infinity of the difference between them is 0, then you can say the two Cauchy sequences are effectively going to define the same real value. in R. And you can do all this, find the difference and everything, and see whether it tends to 0 without actually leaving Q. So this is quite a good definition, as you can see from this. This is the difference between those two, and this is reasonably fast convergence actually. I've had to truncate these obviously because there's like 29 digits in the recurrence part of some of these, and 408 or more, possibly quite a lot in that one anyway. But there it is. Every Cauchy sequence in Q, which of course defines some value in R, can be replaced by an equivalent decimal expansion defining the same value in R. And we saw with pi how easy it was to go from the decimal expansion to a Cauchy sequence corresponding to the decimal expansion. It's a pretty trivial exercise. So they're really sort of like equivalent there. And now actually giving a construction for the decimal expansion from a given Cauchy sequence can actually be a bit tricky, so I'm not going to go into that in any detail, and it's because it's not particularly enlightening anyway. Now a Cauchy sequence in Q of course converges to a value in R, and that's by the definition of what R is, because it's just Q plus all the Cauchy sequences basically. And a Cauchy sequence in R, it turns out, also converges to a value in R, because what you've actually got is a Cauchy sequence of Cauchy sequences, and you can replace each term in the Cauchy sequence by decimal expansion. So then you've got a Cauchy sequence of potentially infinitely long decimal expansions, and then what you do is truncate the nth term to n significant figures. So now you've got a Cauchy sequence which is in Q, and that of course is going to converge to a value in R, and it will be the same value because the difference between the Cauchy sequence in Q and the one in R will tend to 0, because of course as you progress along you're taking more and more significant figures, so the difference will gradually tend to 0. Right, every convergent sequence is a Cauchy sequence, and proof is quite straightforward. If a sequence converges to a limit L, then what you know about it is for all epsilon greater than 0, there exists an n such that the modulus of the difference between xi and the limit L is less than epsilon whenever I is greater than n. So if you take a look at two different values, I and j, say both greater than n, what do you know about them? Well, of course they're greater than n, so of course that condition holds for each of them. And so therefore what do you know about the difference between them? Well, of course that must be less than twice epsilon. Is each of those less than epsilon, so the difference between them must be less than twice epsilon. And therefore it's a Cauchy sequence. Why do I say that? Well, if you give me an epsilon, what I'll do is divide it by 2, and then use that value of epsilon to get a value for n from the sequence, and therefore I know that the difference between any two values greater than that n is going to be less than the epsilon that you gave me. So it's therefore it satisfies the criteria for being a Cauchy sequence.